Cloud networking adds new control planes and distributed traffic paths, which means the security problem is no longer just about where packets go, but also about who is allowed to change the rules that govern those paths. In a traditional data center, networks tend to be anchored to physical devices and relatively stable topology, so the control plane is often limited to a small set of administrators and devices. In cloud environments, networking is defined by software constructs, managed through application programming interfaces, and frequently modified as workloads scale, move, and evolve.
That flexibility is a major benefit, but it also increases the importance of governance, identity, and visibility, because misconfigurations can propagate quickly, and because attackers may target management planes rather than only data plane traffic.
The practical objective is to secure both the virtual network fabric and the administrative mechanisms that create and modify it. Before we continue, a quick note. This audio course is a companion to the CISS books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyberauthor.me in the Bare Metal Study Guide series. Virtual networks in cloud platforms rely on constructs such as virtual private clouds, subnets, and security groups, which together define address space, segmentation boundaries, and permitted traffic flows. A virtual private cloud is the logical container for network resources, providing isolation from other tenants while allowing you to define your own internal routing and connectivity patterns. Subnets divide that space into smaller segments, often aligned to availability zones or functional boundaries, and they become the unit where certain routing and control decisions are applied. Security groups then sit closer to workloads, defining what traffic is allowed to reach or leave an instance or interface, which is a shift from perimeter-first thinking toward workload-centric policy. These constructs are powerful because they make segmentation and access rules explicit in code and configuration, but that also means they must be managed with the same rigor as any other security-critical configuration. Security groups enforce stateful rules close to workloads, and that proximity is a key part of their security value. Stateful rules track the state of connections, allowing return traffic for permitted sessions without requiring you to define symmetric rules explicitly in many designs. Because security groups are attached to workloads, they can implement least privilege at a granular level, limiting which services can talk to which other services regardless of what subnet they share. This helps reduce lateral movement opportunities inside a virtual private cloud because reachability is constrained at the workload boundary, not just at a coarse network segment. The operational challenge is that security groups can multiply rapidly, and inconsistent rule patterns can become difficult to audit without strong naming conventions and policy standards. When security groups are treated as a disciplined policy layer, they become one of the most effective native controls for cloud network segmentation. Network access control lists provide stateless filtering at subnet boundaries, which is a different enforcement model with different strengths and trade-offs. Stateless filtering means each packet is evaluated independently, so you must explicitly allow both directions of traffic when you want bidirectional communication. Because network access control lists apply at the subnet level, they can serve as a coarse boundary control that limits traffic entering or leaving a segment, complementing the finer-grained enforcement of security groups. This can be useful for setting broad guardrails, such as blocking certain ports across an entire subnet or restricting exposure of public-facing segments. The downside is that stateless rules can be more error-prone because missing a direction or misunderstanding ephemeral ports can cause unexpected failures. A mature design uses network access control lists for broad, stable guardrails while relying on security groups for precise, workload-specific controls.
Virtual firewalls add another layer by providing inspection, segmentation, and centralized policy management beyond what basic security groups and network access control lists typically offer. A virtual firewall can perform deeper packet inspection, apply application-aware controls, and enforce consistent policies across many segments and workloads, which is particularly valuable in large environments with complex compliance requirements. Virtual firewalls also often provide centralized management consoles, which can reduce configuration drift and improve auditability when compared with decentralized rule sprawl. In many architectures, they sit at key choke points such as internet egress, ingress, and inter-segment transit paths, providing a place to implement advanced controls like intrusion prevention and content filtering. The key design consideration is placement, because if traffic bypasses the firewall, then the firewall becomes a partial control rather than a consistent enforcement point. When virtual firewalls are deployed intentionally, they can unify inspection and segmentation in ways that native controls alone may not achieve. Cloud Access Security Broker governs cloud application usage, access, and data protection controls, focusing on the reality that many critical workflows happen in software-as-a-service platforms outside your direct infrastructure. A cloud access security broker sits logically between users and cloud services, or integrates through application programming interfaces to provide visibility and enforcement over how cloud applications are used. This is important because users can move data into cloud services, share it externally, or authenticate from unmanaged devices, often without traditional network controls being able to see the full context. A cloud access security broker helps apply policies such as restricting risky applications, enforcing stronger authentication conditions, and monitoring sensitive data movement. The security value comes from addressing cloud usage as an access and data governance problem, not solely as a network routing problem. Cloud access security broker capabilities typically include discovery, policy enforcement, and data loss monitoring, and these capabilities map closely to common cloud risks. Discovery identifies which cloud applications are in use, including unsanctioned services, and it helps quantify shadow information technology patterns that can create unmanaged risk. Policy enforcement can restrict actions such as downloading data to unmanaged devices, sharing files externally, or using weak authentication methods for sensitive services. Data loss monitoring looks for sensitive information moving into or out of cloud platforms, applying detection patterns and policy decisions that reduce accidental exposure and malicious exfiltration. These controls are most effective when they are aligned with identity systems and classification policies, because the same content may be acceptable for one role and prohibited for another. When cloud access security broker capabilities are integrated into broader governance, they become an extension of your data protection strategy into the software-as-a-service layer. Secure Access Service Edge combines networking and security services delivered from distributed points, reflecting the shift to remote users, cloud services, and internet-based connectivity. Instead of backhauling traffic through a central data center for inspection and policy enforcement, Secure Access Service Edge aims to provide security services closer to users and closer to the services they consume. This distribution can improve performance and user experience while still enforcing consistent controls, which is critical when users are not consistently located on corporate networks. Secure Access Service Edge is also a response to the complexity of stitching together multiple point products, because it aims to unify secure web access, cloud access governance, and zero-trust access patterns into a coherent service model. The security implication is that your enforcement points become globally distributed, which requires careful governance, consistent policy definition, and robust logging. When Secure Access Service Edge is implemented well, it aligns security controls with modern traffic paths rather than fighting them. Secure Access Service Edge commonly integrates secure web gateways, cloud access security broker functions, and zero trust access, which makes it useful as a unifying architecture rather than a single feature. Secure web gateways mediate web access, filtering and inspecting outbound requests and providing visibility into destination behavior. Cloud Access Security Broker capabilities extend that control to software as a service usage and data movement, closing the gap where web filtering alone cannot understand application-level actions. Zero Trust Access focuses on granting application access based on identity and context rather than broad network connectivity, which reduces lateral movement and improves least privilege for remote connectivity. The integration matters because it allows policy to be applied consistently across web browsing, software as a service access, and private application access without forcing users through multiple disconnected pathways. In practice, this can simplify operations and improve security posture, but only if you maintain clarity about identity, authorization, and logging across the integrated services. Cloud routing and peering design affects isolation and transitive reachability, and this is one of the most common places where cloud network security either holds or quietly breaks. Peering connects virtual networks, which can simplify communication between environments, but it can also create unexpected pathways if routing is not tightly controlled. Transitive reachability is a particular concern because it describes cases where connectivity through one link unintentionally enables reachability to additional networks beyond what was intended. This can happen when peering relationships combine with route propagation, or when shared services networks become hubs that inadvertently connect many segments. The security requirement is to design routing with explicit intent, limiting which prefixes are advertised and which routes are accepted, and validating that connectivity matches the segmentation model you think you built. In cloud environments, routing is a policy surface, and you should treat it with the same skepticism you apply to firewall rules. Private connectivity options reduce exposure to public networks for sensitive services, which is often a key design decision for regulated workloads and high-value systems. Instead of sending traffic across the public internet, private connectivity can provide dedicated or logically isolated paths between your environment and cloud services, reducing the attack surface associated with public routing and public endpoint exposure. This can also improve performance and reliability by avoiding unpredictable internet paths and by providing more consistent bandwidth characteristics. The security advantage is that sensitive services can remain reachable through controlled private paths while avoiding direct public exposure that invites scanning and exploitation attempts. That said, private connectivity does not eliminate the need for access control and monitoring because threats can still arise from misconfiguration, insider abuse, or compromised internal systems. The value is in reducing unnecessary exposure while maintaining strict policy enforcement on the paths that remain. Cloud logging sources include flow logs, application programming interface activity, and firewall events, and these sources are essential for understanding both data plane behavior and control plane changes. Flow logs provide visibility into network conversations, showing which endpoints communicate and how much data moves, which helps detect unusual traffic patterns and validate segmentation. Application programming interface activity logs reveal who created, modified, or deleted network resources, which is critical because many cloud incidents involve misconfigured security groups, exposed storage, or altered routing. Firewall events, whether from native controls or virtual firewalls, provide insight into blocked and allowed traffic, rule matches, and potential attack patterns at key choke points. The key is to correlate these logs so you can connect a configuration change to a traffic change, or connect an identity event to a network event, which is how you build reliable incident narratives. Without logging across both planes, you can see symptoms but not causes, and that makes response slower and less confident. Identity-based access ties network actions to users, roles, and workloads, and this linkage is a defining feature of mature cloud security. In cloud environments, the ability to change network rules is often governed by identity and role-based permissions, so controlling who can modify security groups, routes, and firewall policies is as important as the policies themselves. Identity also matters in runtime access because services and workloads often authenticate to each other using role credentials, and network segmentation decisions increasingly incorporate those identities rather than relying solely on addresses. When identity is integrated into network security, you can enforce least privilege not just for human administrators but also for services, limiting what each workload can reach and what it can modify. This improves accountability because actions can be traced to specific roles and credentials, and it improves resilience because compromised credentials can be scoped and revoked more precisely. Identity-centered design also aligns naturally with zero-trust approaches, where access is defined by verified identity and context rather than implicit trust. Cloud network security ultimately blends virtual controls with identity and visibility because the environment is software-defined and changes quickly. Security groups and network access control lists provide native enforcement close to workloads and at subnet boundaries, while virtual firewalls add deeper inspection and centralized policy where needed. Cloud Access Security Broker capabilities address cloud application usage and data protection, while Secure Access Service Edge delivers integrated enforcement from distributed points that match modern user and service locations. Routing and peering decisions shape isolation and transitive reachability, so they must be designed intentionally and validated continuously. Private connectivity can reduce exposure for sensitive services, but it still requires strong access control and monitoring to remain secure. When logging covers flow, application programming interface activity, and firewall events, and when identity ties actions to users and roles, you gain the traceability needed to operate confidently. In that combined model, cloud network security becomes a coordinated system rather than a collection of disconnected features. Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.